Okay, good morning, everyone. Let's get started. Do you have any questions before we begin the lecture? All right, assuming everything's all good, then let's continue. So last time we were still reviewing probabilities, almost done. Actually, we touched on most topics I wanted to touch on. The rest we will mention as we cover the statistics, and then we will mention the probabilistic results along the way. But one thing I want to point out is this so-called topic utilizing, uh, you know, known results. I also want to kind of refer to it as working smartly. Okay, and that actually is important for this class because there are many results that you can use to make your life easier when solving a problem in this class. For example, even that theorem of a 2x2 transformation in chapter 7 I mentioned before, if you are aware of it and you can use it, then you just apply and then solve the problem. But if you're not aware of it and you try to solve the problem by scratch, then it's going to be a much harder problem than it really should be. Okay, so anytime you seem to run into some kind of difficult problem in the course, try to see if there's some result that you can use, that you may be aware of or not. Well, of course, the difficulty with this is that your background must be sufficiently rich, right, to quote from results that you know. But a lot of times the results that you need to quote are not that far away. It's just you're not aware that you can use. So let me give you an example. And the example will circle around exponential distribution. All right, so let's say that I have an exponential lambda random variable. Let's just first ask, right, a very common question. Can anyone tell me what the expectation and variance of an exponential lambda is? What are the expectation and variance of an exponential lambda? Okay, 1 over lambda for expectation. And the variance would be? Okay, very good. Now there's a little bit of a tricky thing. For people usually do this, right? But they don't quite specify what they mean, because there are two ways to do it. So so both of you seem to go with this version. What density do you have in mind? In other words, what is the density of the exponential lambda that you have in mind? Well, I guess to prevent, to save time, this is the density you have in mind, isn't it? All right. Be careful, because actually the text, our textbook, okay, when they mention exponential lambda, what they have in mind is this random variable, this density. Okay. Now, of course, the difference is superficial, right? Instead of lambda, you do 1 over lambda. But it is the annoying part where people just mention something and there can be ambiguity when this happens. And so the textbook usually goes with this, so we would choose to go with this in our class. I'm aware that this is also a perfectly viable definition, okay? And there's no rhyme or reason for it. But anyway, if we go with this version, then what should the expectation be then? Then expectation should be lambda, right? And the variance should be lambda squared, okay? So just to, again, just be aware of that small annoying fact about exponential. Anyway, right, this is fine. So let me ask you this. Suppose a question arises on the exam or something that asks you to evaluate the integral of x e to the minus 2x dx from 0 to infinity. How would you do that? How would you do this question? Right, by parts is obvious answer, right? And that's the question, that's kind of the expected answer. By the way, integration by parts is a sort of a default assumption in this class too, that at some point, if you need to do integration by parts, I assume you can do it fluently. Except that by parts is what I would consider a little bit working too hard for this kind of problem, okay? It's perfectly acceptable, but the whole point, right, of being aware of probabilistic results and working in probabilistic context is that just quote things, use things smartly wherever you can. Especially on the exam where you have a million things to do, you don't have the luxury to sit there and just do integration by parts. Except, of course, if that's the only way to do it, then do it, okay? But here there is a better way to do so. How? By exactly utilizing this result. Because what do we know? We know that the integral of 2, right? Let me do this, x e to minus 2x dx, this should be equal to 1/2, right? Because this exactly is expectation of x, where x is an exponential 1/2 by our definition. Okay? Feel free to quote them. If it's a result that is well known, I don't care. You quote them, and I encourage you to quote them, okay? Don't reinvent the wheel. Therefore, the integral that we're looking for, right, exactly is 1/2 of that. So the integral, exactly as Samuel was saying, right, that's going to be, you multiply by 2 to make it into a complete PDF, and you do a 1/2 to compensate out, and the answer is 1/4. No integration by parts involved. Of course, right, that's cheating, because to know this, there's some integration by parts to begin with. But who cares? The work has been done for you. No need, okay? No need to reinvent it. So in other words, right, always keep in mind certain things like the density, okay, the expectation and variance. Identity that can be useful in calculation. All right. You will see this in lecture and in exam. Any questions so far? So maybe let me ask you another question. And this probably for the calculus student will be a little bit terrifying. How about this? Suppose, again, on the exam, this shows up. How would you calculate it? No, you're thinking of the normal, right? This is not. Notice the exponential is only x, not x squared. I'm not sure if that's what you mean. The theme, of course, there are times when the normal will show up, but here the theme is exactly the second moment of the exponential. So Christine, right, what exponential do we have in mind? What exponential do we have in mind? What is x? You need to identify that, right, to be able to do the problem. So the exponential is exponential 2 because it's 1/2, right, in the notation here. Okay, because of the 2 here. Okay, what does it say then? If x, right, let's denote this by x, then what is expectation of x squared? Can anyone tell me? If x is exponential 2, what expectation of x squared? Again, utilizing facts, utilizing things that we know. Not 4. 4 is the variance. All right, that's the hard thing when you exactly 6, not 4, right? Exactly, that is what I'm looking for. It's the variance plus the expectation square, which we know, right? The variance is 2 square, and the expectation. Oh, by the way, the variance is 2 square too, right, Aaron? So I think it's 8, isn't it? 2 square plus 2 square, right? 8, right? You got the idea, but I think you misquote the variance. No, it's fine, perfectly fine, right? This kind of error happens a lot, but you got the right idea. Yes. Okay. But then, right? What is this integral then? Well, to calculate this integral, you just have to line it up with the density. In other words, right? This integral, you do a 1/2, and then do a 2, which is right 2 expectation x squared like this. So the answer should be 16. Is that okay? Again, you see, no integration by parts necessary. Any question? The 1/2, Christine, is to line it up to be a density. That's the trick, right? That's the trick of the trade. Without the 1/2, this is not a proper density. When you write e to x squared like this, what do we have in mind? When we have e to x squared like this, what we have in mind is exactly this integral, right? X squared times the density of the exponential 2. Is that okay? Any question? All right. Oh, no, it's 2. I don't know why it messed up to become an 8. 2, right? 2. 2 to compensate out of 1/2. Yeah. Okay. All right. One last question. Okay. So these are examples to demonstrate the idea. I keep circle around the exponentials, but there are other things that could show up. All right. The theme is to know your result and to line them up. Okay. The last one would be this. Suppose I have a random variable. Okay. Its density will be like this. 6 over lambda e to minus 2x over lambda minus e to minus 3x over lambda for x positive. Okay. This will be a density that comes from the median of the sample median. Okay. We will not be concerned on how it arises. You'll see it later. So the point is just accepting this is a density. Okay. What is expectation of x? What is expectation of x? The question is what expectation of x? Okay. So let's set up the integral. The integral will be right x 6 over lambda e to minus 2x over lambda minus eta minus 3x over lambda dx. Okay. Now, of course, the question is what expectation of x. So how do we evaluate this integral? Exactly, split into two and make two exponential function. Very good, exactly. Right, so the first one will be x, right? But because it's 2 up here, you want a 2 here. So in other words, it's 2 over lambda, eta minus 2x over lambda. Okay, and that's a 3 in front to make up for it. And then the second one, right, you want a 3 and you want a 2 in front. All right. And then you recognize that this is nothing but expectation of exponentials. So this is 3 lambda over 2 minus 2 lambda over 3. Okay. And that becomes lambda, right? 3/2 minus 2/3, which I believe is 5 lambda over 6. Any question? Well, let me tell you, right? This is a real question on the midterm. This is from midterm a year ago, spring 2020. Not to scare you away, but when I give this problem on the midterm, 70 to 80% of students cannot do this question. Okay, so I don't know. I mean, for me, this is a routine question in calculation. Again, right, I am aware that the trick may not be that obvious. And so at that time, I did not mention the trick first time teaching. But you see that the question by itself doesn't have to be really scary or super painful. But of course, right, that 80% of the class approached it via integration by parts. And I would say the integration by parts were rusty as well. So they could not handle it. All right. You could do integration by parts. That's fine with me. Whichever approach you take in this class, as long as it's valid and it gets to the right answer, you get full credit. Okay. But if you choose a painful path to follow and you could not follow it, then that's your responsibility. All right. Once in a while, I would try my best to point out the best approach. But, you know, I mean, we have limited time in class. Okay. But the short thing I want to say is use all the tools in the toolbox, right? Find the shortest path as long as it's valid. Okay. And then make the problems as easy as possible. The questions I gave tend to be more conceptual. The computation should not be too bad, okay? But sometimes you have to see the right way to do it. Any question? All right. So we'll get to see more of this, all right, as we go along the class. So for now, I think we have enough, all right, in terms of the probabilistic review. Let's move on to statistics, okay? So we'll start with chapter 8 today. It's called sampling distributions. Okay. And so to remind you, okay, so what is chapter 8 about? Chapter 8 basically introduces you to the whole like statistical context of the random sample. So a random sample, by a random sample, what we have in mind, okay, is always a sequence of IID random variable, okay? And this IID random variable can come from a distribution. The same, right? Because it's, to remind you, the first I means independent. The second I means identical, so they all have the same distribution. So which distribution are we talking about? So the distribution that's given, right? So the same distribution that they came from, will be referred to as the population distribution. And I will use the letter X without any subscript, right, to denote that generic distribution that all of them follow. Okay, so there's nothing special about the X. In fact, X1 up to Xn all share the same distribution. But sometimes when we have the subscript like this, we may think of, like, the first trial in the experiment. So to avoid unnecessary confusion, we just call big X as the distribution, okay, that everything comes from. And the standout idea is that this X, right, has a unknown parameter theta that it depends on. So theta is the unknown, emphasis unknown, a constant population parameter. And let me put an S here, because there could be more than one parameter that the distribution depends on. And we have seen this, okay? So I'm just putting in the abstract context like this, but we have seen this, right? X1 up to Xn, IID, exponential lambda. So in other words, right, the population distribution is exponential lambda, right? That's it. So all of them come from an exponential lambda distribution. Lambda is the unknown parameter here, right? X1 up to Xn, IID, uniform AB. Okay, so the population distribution is uniform AB, and AB are the unknown parameters. So there are two unknown parameters, A and B. And again, depends on the context and the assumption, right? So this exactly is the part referred to as the model, right? The model of the problem. So we in reality, as I said, right, you basically just have realized value. You have n numerical values from your experiment. And then you say, okay, I will model them as they come from an exponential family with unknown parameter. I will model them as they come from a uniform family, okay, with unknown A and B. But because it's your model, sometimes you can say, well, I will model it so that A is known, like A is 0, for example, only leaving the B unknown. Like, where, let's say, the experiment start or the time start, you don't know where it ends. So the B is unknown, but the A is known, right? So all these things fall into the context of random sample, okay? So the key is that the values of each individual trials follow the same distribution as the population distribution, and they're independent, okay? Our task, or generic task, right, is to say as much as we can about the unknown, right, about the unknown population parameter theta okay, from observing the random sample. And that's it. That's actually the message of parametric statistics right there. In other words, you have a sample, okay? In theory, in what we're discussing right now, we discussed the probabilistic property of these guys, but in reality, right, you would run the experiment and you observe the values. So from the values, okay, from the realized value, in other words, the small x1, small x2 up to small xn, what can you say about the parameters that are unknown, right? The unknown part of your model. Right? This process can be referred to as the calibration of the model, if you want. Calibration. Yeah, calibration of the model. Okay. All right. So um, so the way we do this, okay, the way we do this is via the statistics, sample statistics. Okay, we do this by forming relevant sample statistics. I just say stats, okay, and study the properties. And by properties here, we mean, right, the probabilistic property of these stats. Okay. So the most common stats that we will look at least in chapter 8, okay, are the following: the sample mean, x bar, the sample variance, s square, and the so-called order statistics. So the order statistics means you have a set of numbers, right? These are random. You look at the minimum of those guys, the second smallest value, so on and so forth, until the largest value, okay? These are called the order statistics. So be careful, right? This is not x1. These are the values after you reorder them, right? From the smallest to the largest. So this is basically, if you want, this is the sample min, and this is a sample max, and somewhere in between, right, there's a sample median. Okay, so the point is these guys are random variables. Their properties, okay, what we want to do, we want to state their distribution, if possible, right? Well, by possible here, I mean possible and convenient, okay? Now, one thing that goes without saying is their distribution comes from the model, comes from the population distribution, okay? But the word right here, this distribution, right, is exactly what the book refers to as the sampling distribution. That's the title of the chapter. So in other words, okay, to make the discussion short, basically we have the so-called population distribution, namely the model where you think your sample comes from. There's an unknown parameter, okay? Then you form sample statistics to say something intelligent about these unknown parameters. The sample statistics being, right, formed from random variables themselves is also random. So we want to say something about their distribution. So the distribution of the sample statistics are referred to as the sampling distribution, okay? Now, so those are just a bunch of words, but we will be using them over and over again. And all these things that you have seen so far in maybe statistics or other statistical courses, more or less can be traced back to this sampling distribution. In other words, for example, the confidence intervals, hypothesis testing, right? I'm sure you guys have seen some of those somewhere else, but you may not be aware of where they come from or how you do the things the way you do, the procedure. The procedure that we carry out those, hypothesis testing or confidence intervals all come back to the sampling distribution of the statistics, okay? So studying or being able to say something about the sampling distribution is of foremost importance in explaining, okay, the procedure that we do down the road. So that's just basically telling you the road ahead. Any question about this kind of overall picture? Okay, so we will look at, so the plan, I think for now, let's just focus on 8.1, 8.2 for now, and see if we can move beyond that today. So 8.1, 8.2 basically introduce you to random sample, which we kind of discussed already. And eight point one, 8.2 focus on a sample mean, okay, X bar. And then we move on to a sample variance, and then move on to order stats. So, okay. So the story is, so the question is, right, suppose we have x1 up to xn, IID, okay, from some distribution, some population distribution. And we form X bar, which is a first, statistics that we look at in this class, which is the sum, right, over n. Okay. So by the way, right, again, I will just remind you, when I write the sum without saying anything, it's a sum from 1 to n. What can we say about X bar? Okay, obviously as a random variable. Now, whatever we can say about X bar obviously heavily depends on what this population distribution is. Okay, so let me just put that down, right? This, of course, right, or actually whatever we can say about the sampling distribution heavily depends on what the population distribution is and how they combine. Okay, so that right, so let me just put that down as an observation. Whatever we can say, right, about the sampling distribution heavily, right, depends on what the population distribution is. In other words, your model, right? What is your model? If you make easy model, if you make easy assumption, then the conclusion is easy. If you make complex model, then the conclusion is harder, okay? And also the structure of the statistics. Okay, what do I mean by the second statement? For example, here, the structure of X bar, I hope you realize, at the heart of it is just summing up independent random variables. So that's why I keep harping on summing independent random variables, right, in the previous lecture. If you get a pretty good hold of how independent random variables sum up, then you get a pretty good hold of X bar. Okay, but some other random variables has other structure. For example, the sample variance, okay, as you will see, will be sum of xi minus x bar square over n minus 1. Yes, Derek, exactly. You always know. That's a very good question. In parametric statistics, which is this class, you always know what the population distribution is. Meaning, you know the family, you know it's normal, you know it's exponential, you know it's, I don't know, uniform. What you do not know are the parameters that pin down those distribution exactly. Okay, that's why it's called parametric statistics. There's a very good branch, very strong branch, very popular branch of statistics called non-parametric statistics, which exactly the point is you do not assume the population distribution, or you do not say exactly what the population distribution is. So you obviously, right, that question is harder because you assume less. Okay, that's more advanced. But here we always know. What we do not know is are the parameters. So that's our holy grail, if you want. We want to look for that. Okay, or we want to say something about that. But right, for example, the S square right here, right? Even though you know what the population distribution is, and it's easy, for example, the structure of this guy is much harder than the structure of this guy. In which way? Okay, and that's a discussion, okay, for the next time. But let's just point out, first of all, there's a square. Anytime you square a random variable, you expect that that's a little bit harder than just, plain old random variable. Second, the sum here potentially or actually should be the sum of non-independent random variables. Okay, why so? They're non-independent because each of the summand here has an X bar in it. So they are correlated in some way. So, okay, there's some weird things where these guys may be independent, who knows? But you don't expect so, right? More likely than not, these guys are non-independent. So when you sum them up like this, what are we doing? Okay, so you see the structure of S squared is much more complicated than this guy. But of course, just because the structure is complicated doesn't mean you give up the task and say, I don't want to say anything with this, right? That's the whole point of studying statistics, that you have a complex structure because the object you want to talk about is complex. Okay, you form it, what can you say? All right, so we start with X bar first, and then move on to S squared, and again, all the stats. Each of them has their own peculiar structure that we want to utilize, and then we can say, right, we make statements about their distribution. All right, question. So back to X bar, right? What can we say? So I did not specify the population distribution yet, okay? And there's a reason for that. Interestingly enough, there are always things you can say about X bar without explicitly specifying the population distribution. So suppose, right, the population mean is mu and population variance. So pop, right, from now on means population, okay, is sigma square, okay? So these are constants, but unknown parameters, okay? Constant, but unknown parameters. But, again, right, mu and sigma square can play different role in different distribution. For example, if it's normal, then mu is mu, sigma square is sigma square. But in exponential, right? So for example, if the population is normal mu sigma square, then mu is mu, sigma square. But if x is exponential lambda, then mu is 1 over lambda. Oh, sorry, mu is lambda, right? Following the text. And sigma square is lambda square. You understand, right? So by mu sigma square, we just denote generic population, mean and variance. They can be somehow cast back to the parameters depending on what exactly are the population parameters. Another one would be uniform AB. Then mu would be A plus B over 2. Sigma square will be B minus A square over 12. Is this okay? So right now, okay, I'm not specifying what the distribution is. I'm just saying it's whatever it is with some mu and some sigma square. Then again, right, I form X bar, the sample mean. Then X bar is a random variable. I can calculate its mean, or I can at least attempt to, right? But the expectation of X bar is very easy to calculate because it's expectation of the sum of xi over n. And here, okay, let's spell out the calculation. So first of all, the 1 over n comes out because of the linearity of expectation. Also, the sum comes out because of linearity of expectation, right? So both of these are linearity of expectation. Okay, so that's the bit of probabilistic knowledge you use. Finally, all the xi are identical, okay? So they all come from the same population. Therefore, they all are value of mu, okay? They're all value of mu. So you can replace that with mu like this. So I do this, right? Because some of you already see the next step, but I just do this. So obviously, right, this is nothing but n mu over mu. So that's just n mu over n. So that's just mu. Okay. So the above calculation tells me that whatever population it is, right? The sample mean always has variance mu. Sorry, the sample mean always has expectation mu. Has always expectation equal to the population expectation. Okay. Also notice that the above calculation does not require the independent sample. Independence among xi was not used, which is fine, right? The assumption's there. If you don't use it, it's still valid. It doesn't mean that you don't use it. It makes it invalid. Okay. So this calculation is true whether or not the sample are independent among each other. Okay. Question. Okay. What about the variance? The variance of x bar is the variance of the sum divided by n. Which, right, first of all, take care of the constant. It becomes this. Okay, that's a property of variance. Factor a constant, you get a square out of it. Next, right, there's this bit of the property of the variance that we will quote like this. But this property heavily depends on the independence of xi. Okay, if xi are not independent, this step is completely wrong. So we use the independence here. Finally, right, all the xi are identical, meaning they all come from the same population. So they all have variance sigma square. So I replace each of them by, oh, sorry, I dropped the square, right? And then, so that will be the sum of sigma square like this. Yeah, apologize, I dropped it. And so that will be, right, sum n sigma, sum them up, you got n sigma square over n square, or is sigma square over n. Okay. So again, maybe I won't repeat the writing, but whatever the population is, the sample variance, sorry, the sample mean always has variance x sigma square over n. Okay. So these two statements are universal statement whatever population distribution is. Okay. So there are good statements, right? And actually what you're saying essentially is x bar is a random variable. You have said something about the first moment, and you have said something about the second moment, independent of the population distribution assumption. But of course, right, to say more, that you need more assumption. You cannot say anything. You can say something, but I don't think so. Beyond this, right, the third moment, etc., needs more assumption on the population distribution. So then this is where you start making more assumption and to make more precise statements. Okay. So what I want to say is these statements are universal, but they do not completely identify X bar. Okay. But of course, the value of these statements is true whatever the population distribution is. Also try to see this from the statistical point of view. Why is this valuable? Okay, from the statistical point of view. This is probabilistic point of view. Statistically speaking, this is valuable in two ways. First of all, we alluded to, and we will talk about more, the reason why you care about X bar is because it's a estimator for mu, okay? X bar tells you about mu. So in other words, because mu is unknown, when you form the sample and you observe the sample, realized sample, you say, okay, the sample mean, I will let that be, right, my guess for X bar, for the sample for mu. But how do you know that your guess is good? All right, that's actually the question of statistics. Anyone can form any kind of guess. Your task is to say why my guess makes sense, why my guess is good, or what is the performance of my guess. So if you use X bar or anyone, right, standardly use X bar as a guess for mu, the reason why it's good are twofold. First, because on average, your guess is on target. On average, your guess is on target. That's the first statement. Second of all, the error you commit will be decreasing, right? Will be inversely proportional to the sample size. So of course, if sample size small, your guess is not that good because your error might be higher. Of course, the error also proportional to the error inherent in the population, right? The variation inherent in the population that you cannot control. But if you give, right, me a large enough sample, then my guess is pretty good in terms of the error. It will be quite small, the more sample you give me. Exactly, it's unbiased. We haven't we haven't got there yet, so I don't want to introduce more technical terms. Exactly, that's what I mean by to be unbiased. Yeah. Okay, but try to read statements. Okay, try to read implications out of mathematical statements. If statistics is what you want to pursue, because right, the formula just doesn't mean numbers and symbols. They say something about what's going on out there. All right. Well, I guess since Aaron bring it out, I say, right, this is on target. Exactly what do I mean by this? Precisely. Because, right, you see, the whole point is I have a sample, right? I form X bar. That's my guess. What do I mean to be on target? What's on target here? Is a number. What do you mean to be on? What do I mean to be on target? Does that question make sense? It's a bit abstract, but it's essential for you to understand the business of statistics, right? Or what Aaron said, to be unbiased. What does it mean to be unbiased? Why is it good? Of course, people will quote, okay, unbiased is this. Yeah, so what does it mean? Realistically. So what it means, okay, is it goes back to you have to understand what we mean by saying X bar is a random variable. X bar, right, among one single sample is not a random variable. It's just a number because you already have a realized sample. X bar as a random variable means for every different sample, meaning you keep repeating the experiments, you will get different value of X bar. Okay. So when we say that X bar is on average on target, it means that if you form, let's say, 1,000 samples, okay, from the same population, meaning you keep doing the experiment over and over again, then each experiment gives you a different value of sample mean. okay, because it's random. If you average out all the sample mean, then they will be very close to mu, okay? If you do your experiment over and over again, each experiment, each sample gives you a different sample mean. If you average out all the sample mean, you will get close to mu. Or another way to say, if you want, if you have a large sample size, is that each of these sample, the sample mean fluctuate around the true mean, mu. Okay, that's also what it means to be on target. But they circle around the true mean. But of course, for one single sample, saying on target doesn't make much sense. On target or on average, this expectation statement only comes to life when you repeat the sample 1,000 times. Of course, which doesn't really happen in reality, but we still kind of make that statement to imply what we mean by that. Okay. Any question? Okay. So now let's further our assumption, okay, to make more precise statement on X bar. So actually here, what I mean by this is, let's suppose x1 up to xn are IID normal mu sigma square. Okay. So what do I have that is a little bit more than what I have before? Before I only say mean mu sigma square. Now I say exactly what the population distribution is, which is normal. Okay. Then I think we discussed this before. So that's the beauty of our discussion. We don't have to repeat it. X bar will have a normal with mean mu and variance sigma square over n distribution. Okay, and this comes from the fact that you sum independent normal, it stays normal. All right. So what is the additional detail I have got? Notice that I still get the mean of X bar to be mu and the variance of X bar to be sigma square over n, which is exactly consistent with what I got before. But before, that's where I stopped. Now I go all the way, because now I say, no, not only that, it's a normal random variable. So when I say this, right, I completely specify everything about X bar. Okay, namely the density of X bar is a bell-shaped curve, etc., etc. So there, right, I made that statement. This is complete because I assume the normal distribution of the population. Okay. Any question? Now, unfortunately, this is about the only time we can say that. Okay, and this tells you how tricky the business of saying, you know, something about the sampling distribution is. Sampling distribution in general is not easy to obtain. It highly is dependent on the assumption on the population distribution. Okay, and that's why you see that normal assumption is always behind the scene. It's frankly speaking unrealistic, and you need to be careful when you use that assumption. But on the other hand, it's the one thing we can say precisely. So we just go ahead and say it, and then see how the other statements can be modified when the assumption does not hold. Okay. So an example would be something like this. Let's say x1 up to xn IID uniform AB. Okay. So then I know, right, that expectation of X bar will be A plus B over 2, right? I know that the variance of X bar will be 1 over n times B minus A squared over 12. Is this okay for everybody? Which is from before. What do I, okay, then can I go all the way home? Can I go home with this? Can I say something like, okay, X bar is, I don't know, uniform something something, exponential something something, normal something something. Now I'm going crazy, right? Because I'm just throwing possibilities out. But the question is obviously, right, can I say something about X bar beyond this? Can I? Can I say something exactly about the distribution of X bar? Can I say something about the density of X bar? So first of all, right, let's strike down the obvious. None of this is true, okay, including the normal. Um, so we can, right, derive the density, okay, or the distribution of X bar in this case. But A is tedious unless you know what you're doing, and B is going to be an unnamed distribution. Right. So I want to say this to not to emphasize to you that it's not impossible a task. It's possible. Okay, if you have like 30 minutes to sit there and investigate, you will get it. But it may be a thankless task because you just come up with a density description that frankly is not recorded in the book. By the way, right, there's nothing special about exponential, uniform, that kind of thing. They just are popular models. Okay, they're popular models that keep being used over and over again in different kind of phenomenon. That's why people record them and people know them. Okay, so if somehow the X bar right here under this context becomes super popular in the future for some reason, you can be pretty sure there's some name distribution that's named after it. It's not. So, right, for the purpose of being consistent with the literature, this guy is not something recorded. Okay, but certainly one thing I want to say is none of these guys to begin with. Is none of this. So in other words, this tight, beautiful statement you can make in a normal is not gonna hold in this. And right at the end of the day, it boils down to the fact that summing two uniforms do not give you uniforms. Okay, so that's just that. So this is the exception rather than the norm. Most of the time, we only can say this. That's what I'm trying to say, right? Most of the time, we can only say expectation varies. Beyond that, not much. Let's do another one. Okay. Then I do know that expectation of X bar is lambda. Variance of X bar is lambda squared over n. Okay. From our previous discussion. Do I know anything further about X bar as a distribution? Is it exponential? Is it normal? Is it uniform? Is your quiz, right? I believe your quiz is to be asked if the sum of two independent exponentials give you exponential. Well, I'll give you a spoiler. No, right? Summing two exponentials do not stay exponential. So in fact, right, this is going to be strike down just because the answer is not appropriate. On the other hand, though, you may be surprised to learn that this is a named distribution. In other words, it's going to be a gamma. Okay, with some parameters I don't care to look into right now because that's not part of the discussion. But it is a gamma distribution. Okay, so you're like, wow, really, right? So impressive. Not really. It's just because somehow this is some case where people care about. So they record this, they calculate this, and they give it a name. Okay. But as far as we are concerned, we also group this under the case where too tedious to be careful. All right. But I want to warn you that tediousness or whatever is subjective. It depends on the class, all right? The goal of this class is not to go deep down into this distribution. And so gamma is something that we mentioned in passing, but I would not press you to learn it. So therefore, right, I would group this under, okay, not sure what it is. You see, I say gamma, but I don't say the parameters. But on the other hand, right, if you go to more advanced courses, then this may be a, a precise piece of knowledge you must know. Okay, so to recap, right, what you want to learn about X bar depends on how much work you're willing to go into it. For this class, right, I require you to know this for sure. I require you to know why this is true. And right, I require you to know the normal case. Okay. For the uniform, you at least should know that these do not hold, this and this is true, etc. Right? But beyond that, to be more precise, not really. Or if we go into a specific situation, I'll let you know. Okay. On the exam, somehow I want you to do something, then you do it, but only for that case, not something like. So that's a piece of work that you have to do for the exam, but not because you have to know it as a standard piece of knowledge for the course. Any question? All right. So that begs the question, right? Because then, okay, so seems like the only thing we know, right, is the normal case. Outside of that, we don't know much. We only know the expectation and variance. So there comes, right, this special piece of knowledge called the asymptotic distribution. Okay. This is a special piece of knowledge, or the very, how to say this? There's a very special word that will be keep quoted over and over again whenever you do statistics. Basically, asymptotic distribution, when you hear this word, you can always be pretty sure that sample size is pushed to infinity. Sample size is large. Okay. Now, of course, the tricky bit of knowledge you want to pay attention to is how large. I won't address that. I just want to bring you to the attention that when people push that, it's theoretical. In reality, how large to be close to infinity is always a question, all right? Sometimes 30 is considered infinity. 30 is considered large. We'll discuss that on a different day or, in office hours. But anyway, if you have sufficiently large sample size, then two special things come to mind. The first one is the law of large number. Which say that exactly in our context, if x1 up to xn, IID would mean mu variance sigma square. Then x bar is very close to mu as n goes to infinity. You could say that x bar goes to mu actually, as n goes to infinity. Okay, so be careful, all right? This is a random variable, always a random variable. So when you say it comes to mu like this, you must explain what you mean by that, which is not the point of this class. So I'll just say, right, basically, roughly speaking, if you have a very large sample size, when you form a sample mean, you can be pretty sure that it's so close to the mean, the true mean, that the error is very small. All right, that's law of large number. The second one is a central limit theorem. Where it tries to make this a little bit more precise. Because when you say it's close to mu like this, you're not saying what distribution it takes. Okay, you did not say what distribution it takes. So again, same context, mean mu variance sigma square IID, then I'll make two statements. They're equivalent. The sum of xi approximately has distribution normal with mean n mu and variance n sigma square. And x bar approximately has normal distribution with mean mu and variance sigma square over n. Okay. So you do see that these two statements are the same, right? Because saying that the sum has this normal distribution is the same to say that the bar, which is the sum over n, has this distribution, because the normal is closed under scalar multiplication. All right. So what's the beauty of this? So what is the point of this? The point of this is, notice it doesn't say anything about the population distribution. Whatever population distribution you have, okay? As long as it's IID, it has a mean, it has a variance, then you have this property. In other words, right, the question we were discussing before, right, notice I strike this down. I strike this down because we ask this in a precise sense. Is it precisely normal? No. At no point is X bar precisely normal. Even if n is equal to 10,000, 10 million, it's not precisely normal. But approximately is normal, first of all. And second, in this context, we never even discuss if n is large or n is small. So this has to be struck down generically, okay? But if you're willing to say n is large and you're willing to do approximation, then this is true approximately, okay? So in other words, right, this question has this answer if n is large. This question has a normal answer also when n is large, approximately. And that's the beauty of central limit theorem. You can say generically about any, right, any X bar, the sample mean from any population, as long as you have a large sample size. Of course, right, that is a little bit unrealistic in the sense that a lot of times you don't have money, right, to carry a very large experiment, or precisely the points you only have so much data. But again, that doesn't prevent you from building a theory where things can be said in a simple way when you have a large sample size. So statements of the asymptotic type is worth studying about and is worth keeping in mind. That doesn't mean that it's readily applicable in practice. Okay, so separate these things. But we will see, right, the asymptotic distribution or the asymptotic discussion here and there in this class. And it is a worthwhile piece of knowledge to keep in mind. Any question? Okay, so that finished the discussion on the sample mean. Okay, so do try to see what facts we have talked about the sample mean in the class. So for the rest of the class, 10 minutes, I want to show you some simulation, okay, to demonstrate the idea of random sample. I'll do this once in a while where I can to help illustrate, okay, the idea of statistics behind the scene. So, and the code that I use is Python. Hopefully everyone is familiar with Python, or at least have some familiarity, right? You can just, if you have a Jupyter notebook, you can just import that and run on your own computer. No guarantee on the efficiency of my code, right? I'm not writing like, you know, cutting edge computer code. I'm just demonstrating the statistical ideas. So the first idea that I want to demonstrate in terms of random sampling, hold on. Sorry, somehow I cannot see a chat window. You see my Python code, right? Can anyone say something? Do you see the Python? Yes. Okay, thank you, appreciate it. Let me make it a bit larger. All right, so here I'll simulate, right, a bunch of samples, namely the Bernoulli, the normal, and the uniform. Okay, the uniform is from 0 to 1, normal with mean 1, variance 4. Okay, sigma equal to 2. The Bernoulli has success rate 0.6. Okay, so this is, and sample size is 10. All right, so this is, you know, so by a random sample, you see, this is probably what you're familiar with. You just see a bunch of numbers, right? You just see a bunch of numbers. But behind the scene, right, is a random variable. What do we mean by that? By the way, right, the Bernoulli is a binomial, but only takes 0, 1, right? So this is a trial where you count success, right? So like you have a drug, patient 3, 4, 5 are successful, right? The other patients are failures, right? For example. Notice the range of the numbers makes sense, right? This is between 0 and 1. Normal doesn't have a range, but it should be centering around 1 with not too much large of a spread. Anyway, the point is, right, if I run this sample again, meaning I redo the experiment, right? That's the beauty of computer, it does that for you. Do you see that, oops, do you see that this number changed, right? Maybe it's hard to see, right? But focus on the Bernoulli. Before 111 here, now the 111 changed down to here, right? Run again, right? These numbers change. So that's what we mean, right, by a random sample. Every time you do it, the numbers come out differently. In other words, right, the first coordinate here is a random variable because every time you do it, you do not know if it's 0 or 1. So that's exactly what we mean by a random variable. Hold on, there's a question maybe. Sorry, again, when I do this kind of thing, the chat just doesn't, okay, yes, okay, thanks, all right. So same thing here, right? So each coordinate here is a random variable. Each time and so that's exactly what we mean when we say is a random variable, okay? In this class, we do not care about each of these numbers individually or a realized, right? Because every time I do it, I get a different sense, different outcome, right? The totality of how this usually come out, the rule, the law that they come out is what we mean by random sample, okay? So here, same thing, I repeat, but I basically the code draw twice from the same population, right? To show you that, right, exactly when I draw it twice, the numbers do not have to be the same at all, right? They're two different samples. That's why same population, okay? Same population, but the numbers are not the same. Of course, because these are random sample, okay? And of course, if you do it 10 times, you get 10 different lists of numbers. And here, right, this is a part where I compute the sample mean and the sample variance for you, okay? So here is the normal, that normal population would mean 1, variance 4, or sigma equal to 2, okay? Here's a sample variance, here's a sample mean. Sample size equal to 10. First, I want to demonstrate the idea that sample mean and sample variance are random variables. What do I mean by that? Every time I resample, they come out to be different, right? Let's check. Sorry. So, right, you see the sample mean here is a negative number, even though the true mean is 1. Well, no surprise there, right? It's a random variable. It's a normal random variable. You know, you cannot force it to be anything. Let's run it again, right? 2.16. This is sample variance again, right? The target is 4, right? The target is 4, but it's 2.96. Here, the second time you do it, somehow this is close to 1, but this is 6.27, right? So you see, right? Run one more time. Very different numbers, right? So sample mean and sample variance are random numbers. Okay. Now, sample size here is 10. Okay. How do I make this more precise? How do I get this to converge to 1 and 4? Right, the target is 1 and 4. How do I make this to converge to 1 and 4? Well, by invoking, right, asymptotics, by changing this to, let's say, 1,000. Okay, that's what we mean by large sample. Of course, here I want to force conversion, so I make it very large. In reality, right, I think maybe people don't have money to run 1,000 sample. I mean, a sample of 1,000 size, right? But let's see, if it's 1,000, then you see the sample mean is pretty close to 1. The sample variance is pretty close to 4.4, right? But notice there's still fluctuation, right? There is a tiny bit of fluctuation, but right here, right, there's a fluctuation. But the fluctuation is much less. So that's what we mean by conversions. That's what we mean by conversions, right? That's what we mean by asymptotic. But of course, the realm of the interesting statistics that we study is when n equals to 10, all right? When n equals to 10, everything is random, right? We want to describe the randomness of the outcome like this, okay? When n is large, things boil down to the normal distribution, so and conversions happen, so not much interesting thing happen going on. Well, of course, we still keep that in mind, as a sum statement we can make. Any question here about sample mean, sample variance? Of course, right, once you have the sample, you can form any kind of statistics with it, namely the max, the min, the median, right? And you can observe how they change, okay? Any question? All right. Finally, I want to describe to you the sampling distribution, okay? The sampling distribution. So the easiest way to learn about distribution, by the way, is the histogram. Histogram, if you see it, when the sample size is large, histogram will closely mimic the density graph, okay? Histogram will closely mimic the density graph, okay? As if you have a large sample. So here I'm doing uniform, 0 to 1, and sample size is 2. So I'm looking at the sampling distribution of X bar, okay? I'm looking at the sampling distribution of X bar in this histogram. And I want to compare, right, that with the distribution of the population, which is, X1, right? Because like I said, X1 up to Xn all have the same population distribution. In this case is the uniform 0 to 1, okay? So this hopefully brings home to you that, right, the X bar summing to uniform is not uniform. It has a tent shape, right? The tent is from 0 to 1 rather from 0 to 2 because we already divide by 2, right? I mean, usually the question you see is summing 2 uniform from 0 to 1 to 0 to 1, you get a tent shape from 0 to 2. But here we do X bar, so we divide by 2, so we get 0 to 1. But the shape is a tent shape. Notice it's very contrasting. Also notice that this is not a normal shape, okay? This is too far from normal to be normal, okay? It has that shape, but this is really a triangular shape, okay? Not a normal shape. But the point I want to make is, again, that the X bar, right, and the population distribution are not the same thing. And of course, if you change n equal to 3, right, if you change n equal to 3, you even get a more interesting shape, right? Let's see if I can run it like that, right? You see, now that's the X bar of 3 uniforms, right? A sample of 3 from 0 to 1. So you see, that's the, wait. Sorry, I'm looking at the wrong one. Sorry, this is X bar, right? X bars still stay between 0 and 1, but it looks more like normal, right? But actually, this is a quadratic shape. It's not normal. It's a quadratic shape. Is that okay? So, but then, of course, nailing this down precisely is something I claim to be tedious. It's not that tedious. If you know the pattern, you can just write down. But it's an unnamed distribution that people don't care about. Any question on this? This is for the uniform. So this is sample size 2 uniform, right? It's a tent shape. Of course, you can see central limit theorem going on here, right? If you, let's say n equals to 30, which is usually the golden number when people say central limit theorem starts to kick in, the shape of X bar you see for the uniform starts to look like normal, okay? But of course, right, when n equals to 2, nope, okay? Finally, this is the exponential. This is exponential 1, all right? So again, what I want to show you is the idea that the X bar is not related to the population distribution. This is the exponential, right? This, if anything, shows you that summing exponentials do not stay exponentials. This is a gamma shape, okay? So like that, okay? This is exponential. This is non-exponential. But of course, if I push the n to be large, it starts to pick up the normal shape, right? Maybe let me do 5 for you, right? And then of course, if you say at 30, that golden number for some reason, right? Pretty decent. That's central limit theorem for you right there. Notice how the variance also starts to shrink, right? Notice the variance starts to shrink, okay? Because it starts to be more and more compact. That's sigma squared over n for you right there. Okay, that's sigma squared over n for you right there. Before it's spread out, now it starts to shrink. Any question? So again, right, the code is there for you to play around with if you want. But I just want to demonstrate, right, the idea. This class is completely theoretical, all right? We do these things on paper. I think once in a while it's helpful to bring this thing to life so that you see, right, exactly what we have in mind when we talk about randomness. The randomness exactly is when I hit the run, I get a different picture, different outcome, different output for all these things, right? And we want to capture the law of what I get in general when I hit that run button. Okay. Any question? Okay, very good. Then have a good day then. I'll see you on Friday. Okay. Thank you.
Thank you, Professor.
Thank you. You too. You too. You too.